So, in the basics of limits in calculus, you're going to see basically 4 types of limits. I'll be going through each of these with examples and I guess a description of it with work at a pizza place and a practice problem. So, let's begin with the first type of limit. The first type of limit is one where you can simply plug in the number into the function in order to get the limit. This is something you would do for most functions and most limits. That is basically just your first step. Most functions, you can solve their limits just like this. I'll give you an example. Let's go to the kitchen at work at a pizza place. There's a certain amount of supplies that is given to you at the beginning of the day. Around 30, I guess. As the day goes, that amount decreases until it hits 0. You, wanting to find out what the amount of supply would approach at specific hours, decide to write a limit. You find out that the function for the amount of supplies that are available in a given hour is f of t, which is equal to 30 minus t squared, where t is the amount of hours since opening, and f of t represents the amount of supplies in that hour. Since the restaurant is pretty busy halfway through the day, you would want to find out what limit would the supply reach at 5 hours, kind of as, I guess, preparation. So, using the template from before with a limit, you'd write it out like this. Limit, lim, as your variable approaches some number. In this case, it was 5 hours. T approaches 5. And then your function. Like I said before, for most limits, you would simply just plug in what your variable approaches, and then you could find out what the limit equals to. Let's try it with this function. F of t is equal to 30 minus t squared. When we plug in 5, that is equal to 30 minus 5 squared, which is equal to 30 minus 25, and that is equal to 5. So, that means our limit is equal to 5. Pretty simple. These types of limits are pretty common, and to be honest with you, you are going to be using this method as your first step for evaluating functions. This is something you're going to do no matter what limit you see. So you always do this first when evaluating limits. You just plug in what your variable approaches. Second type of limit that is a little bit more complicated and requires some doable algebra skills with factoring. Let's go back to the kitchen. This time, let's work with how many average points you get. When you make pizzas, you do so because you get in-game points. So, you being someone who wants to optimize the amount of points you get, you decide to find out how many points you get on average per pizza. First, you find a function that represents the total amount of points you get for X pizzas you make in a day, which is f of x is equal to x squared minus 25, where x just is how many pizzas you make in that day, and f of x represents the total amount of points. So, to find the average of that, you take f of x, which is x squared minus 25, and you divide that by x minus 5. And remember, x represents the total amount of pizzas you make. The reason why I'm subtracting 5 in this case from x is because I'm just assuming 5 pizzas won't count towards your average since they are from your bonus hours. And you end up making another function that's called a rational function. And we'll say this is equal to g of x, where this represents the average amount of points you make per pizza. You being a smarty, you decide you want to find out specific averages for different values of how many pizzas you make in a day. And you want to find out which one would get you the greatest average amount of points per pizza. You just plug in random points and you take limits of random values, and you take the limit of the amount of pizzas that you make approaches 5. So you want to see what the average amount of points would approach as you approach 5 pizzas you make in one day. X squared minus 25. Remember to write your function. the first thing you do, you would plug in the number that your variable approaches into the function. So let's go. X approaches 5. Let's just plug in 5 for this limit. 5 squared minus 25 over 5 minus 5. This would be equal to 25 minus 25 over 5 minus 5. That is equal to 0 over 0. So our answer would be 0, right? Well, not exactly. In calculus, this is an example of an indeterminate form. Mathematicians have not decided what numbers divided by 0 would equal to, and it is unclear on what it would equal. For these types of limits where you get an indeterminate value, where you cannot find out the value that it approaches, you have to do something a little bit different. Let's analyze this here. The only reason why we're getting this problem is because our denominator right here is equaling to 0 when we plug in 5. So let's see if we can get rid of that with factoring. We can factor this top numerator and see if we can get rid of the denominator through canceling each other out. The way we would do this, if you notice here, this is a difference of squares, and we can write it as such. Remember, for any two difference of squares, a squared minus b squared, you can write that as a plus b, a minus b, where you can write them as the sum and the difference of each other multiplied. So let's go back to our function, x squared minus 25 over x minus 5. Take a look here. Square root of x squared, in this case, would be x. A would be x. So we write this as x plus something, x minus something. And in this case, our b squared is 25. What's the square root of 25? That's 5. So we put our b into our expression. Then we divide this by x minus 5. And look at this here. We see an x minus 5 appear in the numerator and in the denominator. And because x minus 5 is being multiplied in the numerator, we can cancel these two out. And we can say that it is equal to x plus 5. Now, we can say that this limit would equal to the limit as x approaches 5 of x plus 5. And let's do what I said before. Just plug in what your variable approaches. This is equal to 5 plus 5, which is equal to 10. And that's your answer. A little bit on how this would work out and why you can just simply cancel out the denominator to try and find out your limit. Let's graph that function, that average function. Your function would kind of look like a line right here. And at 5 hours, you see that this graph would kind of align with 10 points, right? But however, like we tried before, when we plug in 5, you get an indeterminate value. So actually, when you're graphing this, you would see a hole here where there's no point specified. Just because a function does not have a value defined in itself doesn't mean that its limit can't equal to that value. So what do I mean? Look at this. When we're coming from the left side right here, we can see that we clearly approach 10. And when we come from the right side too, we can see we also clearly approach 10. Even though the value 10 isn't in the function, the limit still exists because we're approaching 10, and that's the definition of a limit. It's just what value a function approaches. So that's why we can simply just cancel out this denominator and just rewrite this as a limit as x approaches 5 of x plus 5. The third type of limit is also very common, and I use this to explain limits in my short. However, this requires a little bit more thinking instead of math, which can be good news to some of you, but also bad news. So I'll talk about it. Let's take this to the extreme. Remember my example with the amount of pizzas you make per hour as P of T? Let's say you want to find out what is the absolute max. What amount of pizzas can you make per hour when you're extremely burnt out? I mean, when you're overworked to the extreme. Well, you remember that limits just represent values that a function approaches. So, you being a little bit crazy, you take the limit of this function as the amount of hours you work approach infinity, where you are going to be very, very burnt out if you were to actually do this. So, to use this example, you try to hone this function to be 3 minus 15 over t instead of our previous example. This better represents the average amount of pizzas you make per hour. Okay, now remember what I said before? Again, we will just plug in what our variable approaches to find out the limit. But how do you plug in infinity into a function? What would 15 divided by infinity be? That's not clear. So we have to think about this in a different sense. Now, a quick reminder that for limits, if you have something like this for a limit where you're subtracting two things, you can write that as two individual limits where x approaches a of f of x minus the limit as x approaches a of g of x. That would equal to this big limit here. So let's do that in this example. We have two functions here. We have a constant and we have 15 over t. So we can rewrite this as two different limits. Limit as t approaches infinity of 3 minus the limit as t approaches infinity of 15 over t. This is just a constant. So no matter what value you have in your function, it will always equal to 3. So this limit is just going to be 3. However, this is where we had the problem from before. Let's go into Desmos and look at this a little bit more carefully. So I'm going to use an example, a classic example. F of x is equal to 15 over x. I'll actually use t because that's what I'm using here in the example. So this is what our function looks like. Check it out. Notice how this is starting to approach 0. It's getting very, very close to 0. See? And when we zoom out, you can barely tell the difference between the function and 0. And let's look at this algebraically. F of 50. What is f of 50? F of 50 is 50 hours. You have 0.3. Okay, what about f of 100? 0.15. Now let's take it to the absolute extreme. 100,000. 0.0015. As you plug in bigger and bigger numbers, you get more and more closer to 0. Remember what the definition of a limit is? It's a value that a function approaches when a variable approaches another value. We're approaching infinity, and we notice that as we're going more and more closer towards that value, we're getting more and more closer towards 0. So we can just say this is equal to 0. This limit is equal to 0 because we're getting closer and closer for this being 0 as we approach infinity. So this limit, this big limit right here, is equal to these two smaller limits, and these two smaller limits are equal to 3 minus 0, which is equal to 3, and therefore our limit for this big function right here is equal to 3. So that's basically saying you are going to flatline at 3 pizzas per hour in production when you are absolutely burnt out to the max. I want to show you guys something. Let's just go outside of our example and use this for any number. I'm going to say that number is going to be a. Let's add that. I want to make it 7. Notice how our function has the same behavior. It approaches 0. A is equal to 15. Like our previous example, it approaches 0. 30. It goes to 0. 0. It's just 0. So we can say the limit as x approaches infinity of any number n, divided by x is equal to 0, we could say that as you divide a number by infinity, it is getting more and more and more and more and smaller. And it gets so small to the point where it is basically negligible in terms of value. Hence, why we say this is equal to 0. Just a fun fact. There is the fourth type of limit where it doesn't exist. Where you're going to get a value, or where you're not even going to get a value for the limit. Like before, this type of limit requires a little bit more thinking and a little bit more visualization. So I'll give that to you. Let's say you have some clanker that's working at the cashier station. You represent this as a piecewise function, where f of t, this represents the amount of orders you have per hour. So, as I mentioned before, you have the robot working from when it opens to the halfway time. So, this would equal to 10 orders per hour when t is between these numbers, between when it opens and halftime. However, check this out. It goes to 5, it goes down to 5 when a human cashier comes. And he works until the store closes, which is 9 hours. Let's think about this function. If we were to graph a function like this, it would look somewhat like this. It would just be some flat line at 10, and it will be another flat line like this. This is going to be 5 hours for our reference. This is 10, and this will be 5. Okay. The definition of a limit is a value that a function approaches. Let's look at the left side of our function. We can represent the limit of this left side as limit as t approaches 5 minus. This minus basically just means the left side of your function. Well, we see here it's going to be 10 because we go more and more to the left and it stops at around 10 orders per hour, right? So you can say the limit as this. Pretty sure, yeah, f of t, sorry. This is going to equal to 10. But what about when we come from this side of our graph? It goes more and more closer towards 5. So the limit as our function approaches 5 from the right side, 5 plus, that's going to equal to 5. But wait a minute. For the limit of a function at a specified value, I said it has to approach a specific value, one singular value, when you're approaching it from both sides. But we see here, from these two limits, that's not the case. Since that nullifies the definition of a limit, we say this type of limit does not exist. This just means does not exist. And you can't find any limit for this type. That's because look at this here. There's a great gap between these two rates, and it doesn't approach a clear value. So that's it for this video. Soon I'm going to be making a video where I do a bunch of limit problems, and you guys can follow along and practice with me. This video was kind of, I guess, just a general overview and an introduction to these types of limits and what you could see. So thank you guys for watching and enjoy the rest of your day.